thank you very much for coming out and listening to my talk. I am very new to the NERF world, neural rendering world. So you're going to get something more of a philosophical talk, but hopefully it's useful and gives us something to think about. And so I'm going to really talk about what we need to do in order to make robots learn from demonstration. And so so really this title is meant to just give a sense that I believe probabilistic inference is ready for a comeback, but enhanced by neural rendering and neural networks. And so with that, does anybody know what that is that I'm showing on the screen? Those little pieces, little parts there. Anybody know what that is? Any guesses? You can just say it. I have parts. What's that? It's a mouse, but is there a particular mouse?
Tom and Jerry.
Tom and Jerry. Oh my goodness. No, but I appreciate the guess. Give this person points for guessing. I appreciate that. Anybody know who this particular mouse is? Pinky, of course. So if we connect these together and we basically think about the messages that those different part recognitions would give us, then we don't need the whole object. We can just sort of fill in the details. And this is sort of how we've been approaching robot perception for some time. And so just as a note, I lead the Laboratory for Progress, the Laboratory for Perceptive Robotics and Grounded Reasoning Systems at the University of Michigan. That's my group. We all took a great picture here in Philadelphia. And really what I'd like to see by the time my career is over, I'd like to see us have robots that can be programmed fluently by human users through demonstration and instruction. So no more I catching up something and do it in ROS and I have to program in C. I just want to go up to a robot the same way that I would go up to another person and say, let me show you how to do something, and the robot can do that task just by showing it. And so that really is sort of our long-term goal. That's what we're trying to achieve. But I think in order to do that, what we need is really good, robust robot perception. And that robot perception can't just be, I found the answer and it just works. I don't think that's actually gonna be what we need. Actually, I think we're going to have something that maintains probability distributions, so we can get so we have estimates of robot states. The robot state of its world is going to be at best explainable, so we know what's going on, but at minimum diagnosable, so that we have a sense of the probability masses and the modes, and we know what's going on in these systems. And so this is where our group is trying to bring together probabilistic inference with neural networks so that we can get better, more robust estimates of the world, and that's going to enable learning from demonstration. But one battle that's happening in my lab all the time is, do we need object geometries for robot perception? And I'm an old school guy, and I'm like, yeah, geometry, we just collect a bunch and we'll just use it. We'll use particle filters, non-parametric leaf propagation, and it'll just go. But increasingly, maybe we shouldn't do that. Maybe there is a way to better bring these ideas together without having massive databases of robot geometries. And so that gets to what I call this dilemma. Anybody know what that is? Who's that? Say a little louder. These are Reese's, right? So I call this what I'm calling is the Reese's dilemma. And so what I mean by that, I'm gonna play a video. It's my only video with sound. And so if there's one thing that you should take from this, I think this video, this kind of gets to it.
Chocolate.
Peanut butter.
Hey!
Oh, hey, you got your chocolate and my peanut butter.
Peanut butter on my chocolate.
What?
Delicious.
Two great tastes that taste great together. Reese's Peanut Butter Cups. Real milk chocolate, delicious peanut butter.
Reese's Peanut Butter Cups.
And Reese's Crunchy Peanut Butter Cups.
So what do I mean by that? I think one of the big challenges for robot learning is, should the peanut butter be in the chocolate or the chocolate be in the peanut butter, right? And how you combine these things together makes a big, huge difference, right? It's not going to taste the same. And so what I'm really saying by this, I don't know anything about making food, so I don't really actually be peanut butter or chocolate. What I actually mean is, should the probabilistic inference be in the neural network? And we see a lot of that, right? We see a lot of LSTMs and filtering inside of neural networks and message passing inside of neural networks. If you go around the conference, you see a lot of those ideas. But I'm going to make the alternative argument. I'm going to make the argument that the neural network should be inside of the probabilistic inference. The neural network should give you should give you recognitions on sort of, let's say, the front end, and then we use probabilistic inference to actually use those to form probability distributions, maintain multiple hypotheses that are explainable, that are generated, that can be diagnosed. And from that, that's where we're actually going to get our inference. That's going to get our belief state that can then better inform planning or other types of decision making we have to do with the robot. And so with this, so that's the main point that I'd like to make. That's what we're exploring. Neural networks inside of probabilistic inference. But to give some context about what this looks like, I'd like to just give a quick overview of where we're going in terms of learning from demonstration. So learning from demonstration is really about, we want objects that we have to work in human spaces. That means we've got a wide diversity of objects that are in cluttered, weird configurations, occlusions all over the place, all types of affordances, all types of semantics that we have to infer on top of these objects. And we have to do that. We have to use those to do something purposeful: cooking, cleaning, repair, assembly. There's a number of things. There's the form and function semantics of all of these objects are really important. By the way, keep me on time. This is unrehearsed. I made these slides at 6 o'clock in the morning, so you have to keep me on time. All right, but we have to use all of these objects in context, and our perception systems have to be able to give us the estimate of the state of our world in order to do this. And if we can get that estimate of robot state, then really what we're trying to do in terms of learning from demonstration is to be able to teach any robot, any variable robot, to perform any variable task in any variable environment. And even just trying to get this to work in somebody's kitchen, definitely my kitchen because my kids are messy, is a major challenge. And that really is where we want to be able to see long term. There's many different approaches to accomplish this goal. Learning from demonstration is only one. You could use traditional programming, cognitive architectures, natural language processing. There's many. So really, the big question we have to ask is how we're gonna get people to program robots. And these days, if somebody asks what's the ultimate in sort of how we can teach robots how to do things, it's going to be transformers, right? Transformers should be both performant, scale to new tasks, and also be a natural mode of interaction, ease of interaction. So that's sort of your Codex, GPT-3 style approach to natural language for coding robots. But I would say that there are some issues with that. One is even these neural networks are right 99% of the time, if you don't know the 1% of the time that it's wrong, how can you trust any result? You can try to minimize the errors, but if you don't know where the errors can come from, or you can't know when they happen, that's a big problem. And that comes to issues that we see across the board, including issues of facial recognition, ethics, bias, that we see all across the academy. They're being studied all across the academy right now. And so also when we think about who's going to be in the room when we develop these technologies, and those bias issues, and the unfortunate fact is that when I look in this room, there's more diversity here than I've seen in the past over my 25 years in robotics, but we still need to have more diversity because the products that we produce, the people producing those products all of us will have biases. We have to be mindful of that. And so we need diversity in the development. But really what I'm going to make the claim is that the next generation of learning from demonstration is going to be able to be both more performant and more scalable to new tasks. And the way we're going to do that is through combining 3D semantic mapping. And there's a wealth of growing body of literature in how we develop 3D semantic mapping, and combining that with declarative planning-based programming. So I just want to show the robot the goal of what I want it to do, and then it can figure out how to actually achieve that goal. I shouldn't be showing it how to grasp an object, but I should show it, this is the outcome that I want, and the robot can do the task and motion planning on its own. And so we combine these together in terms of what we call semantic robot programming. So in semantic robot programming, what a user does is they go up to in front of a robot and they say, robot, I'd like you to achieve this arbitrary scene in the world. The robot then can go through and perceive that scene, that goal scene. The way we've typically done that is through neural network facial recognitions, just bounding boxes with a pose estimator behind it to just reconcile what the scene looks like. And then from that, we can generate a scene graph, a PDDL style scene graph that represents these axioms that we can then give to a task and motion planning system. Then when the robot comes back to that same environment at a new time where it's all messed up and jumbled, it can do that same perception to then also estimate the scene at this moment in time, build up a scene graph, and then from the scene graph of the goal and the scene graph of what the current state of the scene looks like, it can then do task and motion planning to achieve that goal. And so this is really, the most important part of what we're doing here is that we're not programmed. There's no lines of code that are written in order to do this. We just go up and show the robot what we want, and the robot is doing all the reasoning about pick and place actions, about which order to execute the actions, and how to achieve this goal. And so really what we're saying is the robot, we just want to show the robot what we want done, not necessarily how to do it. So there we go, goal achieved. And so we've been able to do this for a number of different scenarios and conditions. And so this is really starting to be, trust me that this works. We have papers on this, but we can just show the robot what we want to do, and the robot can then do it. But in order to do things this way, in order to do semantic robot programming, we have to do scene estimation and clutter. That means we have to estimate, at least the way that we have our system set up right now, we need object poses, we need inter-object relations as form of scene graph, and we have to deal with uncertainty in the form of occlusions, stacking, off-balance contacts, multiple supports, all sorts of craziness that's happening in the scene. And in general, what I'd like to say is that we should be able to do the scene estimation without the usual crutches that we might see across computer vision or other areas. No green screens, no monocolored objects, no isolated objects, no Coke can sitting on its own. We don't necessarily need AR tags, but the one at the end is, do we still need known geometry? So a lot of our systems require known geometries. But what we've been able to do, assuming that we have known geometries, we could just pour out objects onto a table. The robot will then be able to recognize each object using neural networks and then a particle, in this case, particle filter on the back end to reconcile whether that was a correct recognition or not. And then sort it into laundry items on the left and items that don't go in the laundry room on the right. You'll note that it's putting the comment into the laundry room items. And anybody who knows what they're doing knows the comment goes in the kitchen, not the laundry room. That's not a mistake of the robot. That's because my students don't do a lot of laundry or dishes. So that's their issue. But essentially, we can do this, and we can estimate different types of graph poses. The way that our typical estimation pipeline looks like is we run something like RCNN, this is RCNN out of 2018. That will be the first recognition. We're going to separate false positives by using by essentially trying to estimate with a particle filter, some sort of probabilistic inference, to then figure out to get the distribution over our possible scene that's out there. And then from that, we get object poses, and we get a representation of scene for doing task and motion planning, and also generating graphs. And so that's how this typically works. But suppose we don't need the whole geometry, because that whole geometry is painful to get. What if we only needed part of the object geometry? And could this allow us to better get the best of both convolutional neural networks and probabilistic inference? And so what we're really thinking about when we're thinking about this is that discriminative inference that we get from a neural network has good recall, it's fast, but it's inexplicable. We can't explain the results, which is a major problem. But with generative inference, even if we can do this, it's robust, it's explainable, but it's slow. How can we really get the best of both of these? And a parts-based inference system is one way that we can do this. So when we're thinking about how to bring these together, what we can do is we can represent an object, let's say an articulated object that has many degrees of freedom, as a Markov random field. Hopefully this video is cool. And so what we can do is we can consider the observations on this Markov random field as a heat map of CNNs over different types of parts, not the whole object, but just a part of an object. And so if we can use the neural networks in order to get those recognition of the heat map, then we can use message passing through non-parametric belief propagation, because I believe probabilistic inference is ready for a comeback, to then reconcile and try to get estimates of these types of objects, articulated objects that could be in any type of pose. And so this is something that we can do right now. This is work that we had at IROS 2020. And so this is how we can deal with these types of objects. Oops. But something happened during the pandemic, in that my student said, "Have you seen this INRs work?" And I was like, "What's that? What's a nerf?" And it started a debate inside of our group, which basically said, maybe we don't need object geometries at all. Maybe object geometries are just not really that important. And maybe the way we should think about our problem is that the neural network is actually going to serve as our likelihood function. The neural network is actually going to deal with appearance. It's actually going to take our observation of the world and turn that into what would happen if we generated a hypothesis of the world, what the world looks like. The nerve could generate what the world would be from that hypothesis. So if we say, I'm going to be at Philadelphia in this room, and these are the people that are going to be out here, I should generate what that actually would look like in the robot's image. And neural networks give us that possibility of doing that. But that also allows for our probabilistic inference to then generate those hypotheses that are explainable, that have a process behind them, that we can then verify and understand. And so that's how we sort of see that a way of doing perception of the world without needing object geometry. And so then we dove into the nerf explosion. I thank Frank Dellert for this fabulous survey, and then we just started diving into something that we could do, which is what we call NARF, neural articulated radiance fields. So what we're really thinking about in this case is how can we generate NERF renderings for articulated objects as one possible variable that you might see in a scene. Objects that have different articulations. We also want to consider things like lighting and different types of backgrounds, but really in this case we're only thinking about articulation. So in this case, what we're going to have is a configurable NERF rendering. And what we're going to be able to do is the training that we're giving into the system is both RGB images, pose and segmentations, and also the kinematic structure of the object in terms of URDF. And so this is really meant to be sort of a differentiable engine that we can use to generate renderings of articulated objects. The way that the system works is that we're going to render out every part. We know that the parts together, that each part can be rendered from a neural perspective, and then we're going to use some form of probabilistic inference in order to reconcile these parts together. And then we're going to generate the parts, and then we're going to render them out. We're going to have a layered renderings of each of those parts. And then we can then generate those configurations. I don't actually know fully what I'm talking about because I'm a faculty member that spends most of my time at email and doing presentations like this at a high level. If you really want to know what's going on inside of this, Stanley Lewis is my main student who's working on this. He's around and he can answer all your questions, as well as our co-author Jana Pavlasa. And so that really is sort of getting through our journey. I'm just making this argument that as you're thinking about neural rendering, that it's not just the goal to generate the neural rendering itself, but I would argue you should put it inside of a probabilistic inference engine. And what neural rendering can get you is to say, if I have this hypothesis of the world, this is what it should look like in my observation. And we could get something that looks photorealistic, like really it's just sort of like, this is what the world would be if this was the true hypothesis. And then we can use that for planning moving forward with all sorts of great pre-planning algorithms that are coming up and belief-based planning. And so that's really all I wanted to say. Hopefully I'm on time.
We have 10 minutes for questions.
10 minutes for questions. All right. I was a little too conservative there. But there is one thing that I wanted to say. And so maybe I'll put you back on, I'll leave a lot of time here. Is that I wanted to also say that that the Reese's dilemma also suggests that our community should continually improve to include. I've been very heartened by what I've been seeing at this conference, because when I started in robotics, that was about 25 years ago, and the diversity at the conference has drastically improved. Diversity that we've seen, that even just IROS 2017, I went around and shook the hand of every Black person that I could find that attended the conference, and I was able to do it. There's only a few. Now I have no chance of doing that. Just the gender diversity that is really great to see. And really, when we're looking at this commercial, a lot has changed in the last 40 years. And so one of those things that's changed is we're just aware of a lot more things these days. And I just like to also mention that I have that I'm part of the RES Cares committee, which basically means that for any issues that you may have, any concerns, we're always here to listen, because we don't just generate intellectual ideas and we don't just generate papers. We are a community, and so I'm always here and willing to listen as people have things they want to say. So in conclusion, leaving lots of time, I misestimated in the wrong direction.
It's more like 5 minutes.
More like 5 minutes, all right.
Yeah.
And so really, what we're trying to do in my lab is to enable robots to be programmed fluently by human users from demonstration. And robot perception is a critical part of that. And we may not need object geometries to do that. And I think neural rendering, which is why I'm excited to see this, really it really provides probably the best possible path that I can see. And so inclusion, we're really trying to make fluent robot learning from demonstration. We need to put neural networks inside of probabilistic inference. That is the key here. And NERF is just, I think, the NERF-based methods, I think, are really great. So with that, I'll give 5 minutes back.
So just very quickly, as before, you can enter questions in the chat on Zoom or come up to the mic, and we have like 5 or 6 minutes.
Yeah. So, I'm on board with this vision.
Yeah.
But the part that are the known, we need known geometry, right? I mean, it seems like you still have known geometry. Right? You're still operating on known objects.
Right.
And you're building compressed geometry. And I think, so my real question is actually about the paradigm from step back. We say you want to show the robot models. How does logic work with these things? Why do we even need to show it? Why can't we just tell it maybe in structured language, or we don't need to go to the natural language route, right? In some way that we can actually generalize to novel objects that we express. I think often when we show this is what I want, it's like, I've done it. Why does a robot need to do it?
Right. So I think I would say that we have to enable multiple modes of demonstration to the robot. Right. It could be the case that we can just start speaking to robots. Alexa robot, just assemble the birdhouse, fix the refrigerator, and it should be able to do it. I don't necessarily think that natural language will be the mode that everybody wants to use, and it may not be amenable to certain things that we want to show. Like if you have to show the robot, this is how you do a specific task, and let me just visually show you how to do it. And so we want to enable those multiple modes. I would say for the perception pipeline, the argument is that we still need object geometries in training, but not at query time. And we should be thinking about rendering not necessarily whole objects, but parts of objects. And so I'd make part of what I'm saying is that if we had renderings of parts of objects, we can compose them together, and that will give us more. I believe that will give us more generalizability, and also allow us to model articulated objects.
Okay.
Do you want to follow up on that?
I mean, I still think you still have the geometry of the object you're dealing with, right?
Yeah.
Like if I have a different clamp than the one you have here,
Right.
this isn't gonna work. And like, if I want my robot to build, you said like environment X, environment,
Right.
the variable in the beginning, right? It seems like there's still one variable, which is the object instance
Oh.
is built into all of it.
So I forgot to say this, and this is a great question for Stanley, because Stanley and I, because basically I say, Stanley, how we're going to generalize over a class of objects. So if you have a different clamp, what we have to do is train on multiple different types of clamps, right? And what how do we model and collect data for all the different types of clamps in the class? It's still an issue, and it's not clear that the NERFs will be able to generalize over the entire class. But I think that is what we have debates over in my lab about how we could potentially do that. I think that's a great avenue for research.
Yeah, harassing a student is okay.
No, it's not. But,
No, not in that
I know what you mean, but I wanted to. I can't be on a recording saying that harassing students is okay, but I know what you mean, Tucker. One love. Yeah.
My question is related to what you made in your presentation about knowing that 1% of cases where methods can fail and
Yeah.
being able to say something about that. So within that, the research development paradigm to have it in your talk, regardless of whether the networks in their inference or inference in the network, how do you go about answering those questions about your method? How do you figure out 1% of cases, 0.1% of cases where my architecture is going to not be able to do something or say the wrong thing? And what does that look like for some of the material you presented from your lab?
So I think maybe underlying everything I said is I don't trust neural networks. I would probably never trust neural networks. I believe neural networks are overfitting. And I know that's sort of a lightning thing to say, those are fighting words. But that's what I believe, right? And so the question is, but it's clear that they've shown benefit, they've shown incredible recall power and capability. But the problem is that I just, even with this increasing accuracy, I don't know when I can trust them. So where should we put neural networks into our perception pipelines, maybe even our decision pipelines, so that we can get the most benefit of that from those systems? And so if the network is generating renderings and just sort of saying, this is what your hypothesis could look like, that's okay, as long as I have a process behind it that is explaining what actually was behind the generation of that output of the neural network, right? If I said, I'm coming up to my kitchen table and this is what I believe the state of the table is, and I generate a rendering of it, right? Then if I go back and I try to see there was an error, I can see this is what I believe the state of the system, the state of the world to be. This is what was rendered, and I can diagnose that. I can put liability, and I can put, I can assign culpability or fix that problem. But if I'm doing end-to-end learning, right, then I'm going pixels to torques, and something happens, and then I have to go in and inspect individual nodes, and I don't know what that looks like. That is maybe research, maybe future research will figure that out, but I'm not optimistic that's going to happen.
At the end of the day, what you're doing is just holding your hands up and saying, it's either something's wrong with the input or something's wrong with the output, and I guess we just do better.
So can you elaborate on that?
Well, so like when you're saying that if I see something's wrong in the generative distribution of my network outputting, I can spot it and I can be like, right, cool, there's something wrong here. But at the end of the day, if you want to go fix that, you don't necessarily get information about how to go about fixing it.
Right, but no, so it's not necessarily fixing it, it's being able to diagnose what happened and what went wrong. The fix is going to be the next thing, right? That might be up for my planner to try to fix that. My planner can say, all right, I saw this state that I hypothesized that I thought was the true state actually isn't the true state because I took an action and that clamp or that mug or that object was not where I thought it was. Now I have to reshift my distribution given that. This is what happens with our mobile robots, right? They run a particle filter, they go off, they do something, and they may see, their likelihood may say the world, their estimate of the world is wrong, and so then particles shift and go somewhere else. How can we get that, but beyond just sort of two-dimensional planar navigation? And I think those types of things are really, really interesting questions. Thank you.